Welcome back to Calculus Conundrums, Applications of Derivatives by the Perfect Square. Feel free to subscribe if it strikes your fancy. The concavity of a graph has to do with the curvature of the graph. So if you take a look at these two graphs, the curvature is, as you go left to right, they're trying to curve upward. So in other words, if it appears the graph is curving in a counterclockwise fashion, then we call this concave upward. So this graph is trying to curve counterclockwise, and this graph is trying to curve counterclockwise. So notice you can have concave up with either increasing or decreasing functions. And likewise, you can have concave down with increasing or decreasing functions. So here, at least over here, this function is increasing. So it's increasing and it's concave down. And so when it's concave down, the curvature is clockwise. So the curvature is turning clockwise here. And so both of these are concave down. Now, a graph can actually change concavity. If you'll notice, whoops, what happened? Just a second. Sorry about that. I hit the wrong button. So if you'll notice this right here, this graph, this portion of the graph, it has the counterclockwise curvature. But then over here on this side, the graph has a clockwise curvature. So what happens is there's somewhere in here the graph had to change from concave upward to concave downward. And that point there where it changes, the point on the graph where the concavity changes, is called the point of inflection. So that's point of inflection. Now, this is just the definition of concavity, and it says that f be a differentiable function over the interval I. The graph is concave upward if the derivative is increasing, and the graph is concave downward if the derivative is decreasing. Well, I'll try to tie this together for you so you'll know why we check the second derivative. So let me put it this way. Concave up implies the first derivative is increasing, right? Isn't that what it said? Concave up, first derivative increasing. All right, but we know if the first derivative increases, it implies its derivative is positive. Now, I'm not talking about the first derivative. I'm talking about the derivative of the first derivative. So what would be the derivative of the first derivative? That would be the second derivative. So the second derivative would be positive. So, long story short, concave up means that the second derivative is positive. Now, in a likewise fashion, concave down means that the second derivative is negative. So this leads to a test for concavity. The way you test for concavity is you find the second derivative, and you determine where the second derivative is positive, and where the second derivative is positive, the graph is concave upward, and then determine where the second derivative is negative, and then the graph is concave downward. Okay, so I'll just look at this example here. You see this portion of the graph here. Again, it's got that upward concavity. So here, on this side, the second derivative, I know the second derivative has to be positive. But over here, on this side, the curvature is a downward curvature. So I know over here, the second derivative must be negative. Okay, now the definition of a point of inflection basically says if C is a point of inflection, if f of C is a point of inflection, then either the second derivative has to be 0 at the point of inflection, or the second derivative does not exist at that value. Okay, so this simply tells us that we must identify values where the second derivative either equals 0 or is undefined to find points of inflection. So there's the key to determining concavity. find where the second derivative is 0 or undefined. And those will be possible points of inflection, but we won't know until we test them. So this one here says, let's discuss the concavity of this function. Okay, so what we're going to need is, we're going to need the second derivative. So the first derivative, take the derivative of this, and you'll get 4x cubed minus 12x. Now the second derivative would just be the derivative of the first derivative. So take the derivative of the first derivative, and you get 12x squared minus 12. Now, so that's the second derivative. Now the second derivative can equal 0, but it's not going to be undefined since it's a polynomial. So all I really have to do is find when does that second derivative equal 0. So set that second derivative equals 0, and I can factor 12 out of these, and I get 12 times x squared minus 1. Then you can set x squared minus 1 equals 0, and you can see that the second derivative equals 0 when x is minus 1 or plus 1. So I'm going to create a table very similar to what I did when I was studying extrema and increasing, decreasing, but I'm not going to test the first derivative this time. Now, this is important. I'm not going to test the first derivative. I'm actually testing the second derivative here, because I want to know if the second derivative is positive or negative on these intervals. So what I'm going to do is, I know that these are my possible points of inflection, x equal negative 1 and 1. So I'm going to break my number line up at negative 1 and positive 1. Okay, and so to the left of negative 1, I pick a test point, negative 2, and notice I'm plugging it into the second derivative here. There's two little marks there. So plug negative 2 into this, and you'll get 12 times a positive number, which is positive. So that tells me that the graph is concave up on this interval. So on the interval negative infinity to negative 1, the graph is concave up. Now test the next interval. So I'll pick a number like 0 in here, and I'll plug 0 in here, and that'll give me 12 times minus 1, which is negative. So that since the second derivative is negative, then the graph is concave down on that interval. And then likewise for the third one, I choose a number to the right of 1, like 2, and plug 2 in, and I get a positive for the second derivative. And since the second derivative is positive, it's concave up. And then I summarize it down here. The graph is concave down on negative 1 to 1 and concave up on the other two intervals. Now, the point of inflection is the point negative 1 and f of negative 1, and the point 1 and f of 1. Now, I didn't give the y value there, but it actually shows you on the graph here. If you look at the graph, you know, you may not know, you can kind of see over here, that it's concave upward, and then in here it's concave down, and then over here it goes back to concave upward. But you might not know exactly where the change occurs. Well, from our study here, we know the change occurs at negative 1 and then the corresponding y value, and that's actually negative 1, negative 5. And the other place it occurs is at the 1 and its corresponding y value, which is 1, negative 5. So it changes here and here. All right, and so those are called points of inflection. Okay. Now take a look at this one. I'm going to assume now that you know how to find derivatives of polynomials. So to discuss concavity here, I'll take the first derivative and get minus 12x squared minus 16x, and the second derivative is minus 24x minus 16. Now set that equal to 0 and solve it, and we get a possible point of inflection at negative 2/3. Now all I have to do here, since I only got one possible point of inflection, I'll just draw my number line, and then let's see, that breaks here at negative 2/3. So this is at negative 2/3. So that represents negative 2/3. Now pick a number to the left of negative 2/3, like negative 1. Plug that into my second derivative. Remember the second derivative. So that would give me 24 minus 16, which is positive. And then pick a number in this interval greater than negative 2/3, like maybe 0, and plug that in, and I get a negative number. So the graph is concave up on the first interval, and it's concave down on the second interval. And also, whatever the point is that corresponds to x equal negative 2/3 and the y value f at negative 2/3, that's the point of inflection. Now if you look at the graph, I kind of copped out here. I didn't calculate the y value because it's kind of weird, but you can plug, if you had to have it, you just plug negative 2/3 into this original function and try to get a common denominator so you can write it as a fraction. But anyway, the point is right here, right there. And you can see to the left it's concave up, and to the right the graph is concave down. All right. Okay, I'm going to do a couple more real quick. Y equals x over x minus 1. Okay. Go ahead and find the first derivative, then take the derivative of the first derivative and show the second derivative is 2 over x minus 1 cubed. Now, f double prime is undefined at x equal 1, but so is the original function. So I know I'm not going to get a point of inflection at x equal 1, but let's go ahead and talk about the concavity. The concavity could change across that vertical asymptote. So let's go ahead and check the concavity on each side of that vertical asymptote. So this vertical line represents x equal 1. Now if you pick a number to the left of 1, like 0, and plug it into this, you'll get a negative number. And then if you pick a number like greater than 1, like positive 2, and plug it into this, you get 2 over 1 cubed, which is a positive number. So the graph is concave down to the left and concave up to the right of 1. So that's the intervals where it's concave down and concave up. And so 1's not in the domain. See, this would be, 1 would be a vertical asymptote, trying to draw it for you here. But you can see that on this side of it, it's concave down, and on this side of it, it's concave up. All right, one more. Y equal 2x minus tangent x. Show that the second derivative here is minus 2 tangent x secant squared x. And so the only way that that can equal 0 is if tangent x is 0 or secant squared x is 0. And by the way, I'm only looking at it from negative 2 to positive 2. So here x equals 0, that would be the only place. Now the domain is that the cosine cannot be 0, so because that would be, remember, tangent x is sine x over cosine x. So if cosine x cannot be 0, we also know x can't be plus or minus pi over 2. So basically I'm going to break it at minus pi over 2, at 0 because that's where the second derivative is 0, and at pi over 2. Okay? Now I'm just going to abbreviate this. I take a value from each one of these intervals and plug them into the second derivative. And when I plug each of these values into the second derivative, this one gave me a negative, so it's concave down there. This one gave me a positive, so it's concave up there. This one gave me a negative, so we're concave down here. This one gave me a positive, so we're concave up there. Well, let's look at the graph real quick. Notice that this was a vertical asymptote. That's x equal minus pi over 2. And another vertical asymptote was x equal plus pi over 2. And notice it's concave down here, and then it's concave up over here till you get to 0, and then at 0 it changes back to concave down, okay? And then on this side of this vertical asymptote it goes back to concave up, so that corresponds with my table. And notice the concavity changed at 0, 0. So 0, 0 is the only point of inflection. Even though the concavity changed across these asymptotes, an asymptote cannot be a point of inflection because asymptotes are not points. So that's how you discuss the concavity of a function. And there are some others here. You can practice on these if you want to.